Hey, chemistry. On to a new unit and a new chapter. Unit's going to be chapter 2, 13, and 14, talking about matter. We're going to start out with properties of matter. Big giant question. How can we describe matter and its properties and changes? So let's get started. All right. We're going to think about what you observe when you look at a particular sample of matter and its properties. Do you look at a solid and say, is it shiny or is it dull? Do you have a liquid that flows really quickly like water or really slowly like syrup? Is a gas odorless or does it have a smell? There is a difference between, smelling just regular air and smelling what's entered the air when somebody hits a skunk. So yeah, that's a difference. That is, a skunk lets out when it gets hit by a car, that is not odorless. We have two types of properties, and I kind of touched on this already with density. Extensive properties tie in with matter. Matter is, again, anything that has mass takes up space. It's a measure of how much mass is a measure of how much matter the object contains. We talked about the difference between mass and weight. Mass of a basketball. I'm blocking one of my images here. The mass of a basketball is greater than the mass of a golf ball. But do they occupy the same volume? That's going to be just a little different. The volume of an object, that is measured by the space occupied by the object. Obviously the volume, the basketball takes up more volume than the golf ball. And if you divide mass by volume, you get density. But we learned earlier, density is intensive, and that's what I'm going to get to in just a second. Mass and volume are extensive. These properties depend on what's in the sample, the amount of matter in a sample, as in to what extent do we have this stuff. Looking at volume, mass, size, weight. Again, remember our endless debate of mass versus weight and length. As in, what matters is how much of it we have. Now, again, mass and volume, we could think about intensive. We could think about a density. We could divide the mass by volume to get the density of that basketball. There are several properties to consider. Outer covering may be leather, rubber, or some kind of synthetic composite, some kind of polymer. Each of those materials will have different properties to make the basketball suitable for different playing situations. Absorbency, color, odor. Notice the British spelling too. All these different things here. These are intensive properties. It depends on what's in the sample, and density is one of those. Because we could have a sample of any size, like say like a little bit of copper or a mountain of copper. It would still have the same ductility, the same relative ability to be pulled into a wire. It'd have the same luster, same melting and boiling point. It depends on what's in the sample, the intensive properties. Remember, extensive properties, it depends on to what extent do I have this stuff. Intensive depends on what's in it. It's a good way to try to remember those two. Now, each object in this figure, can of Dr. Pepper and a nice copper-looking watering can, something decorative that you might have around the house. It's made of a different chemical makeup or composition. Soda cans, mainly aluminum. Watering can, mainly copper. They're obviously based on two different elements. And when we talk about something like these being mostly aluminum, mostly copper, there we go. Matter with a uniform and definite composition, as in it kind of looks the same. And we study a little farther, it is pretty much the same composition. We call it a substance. Aluminum and copper, we consider them pure substances also, because those are two examples of pure substances. Every sample of a given substance has identical intensive properties, because every sample has the same composition. If we were to take a sample of aluminum and from the R in Dr. Pepper, or down here on this side, you'd have probably the same density, same chemical makeup. This same makeup as the spout versus the main part of that watering can. Again, they have some properties in common. They're both metals, but there's some differences besides their distinctive colors. We didn't have that Dr. Pepper wrapper. We see something that's kind of silver looking. Aluminum is highly reflective, often used in silver paint. If Pure copper can scratch the surface of aluminum. This is something I'd talk about in Earth and Space Science. Copper is on the hardness scale. Copper is harder than aluminum. You can take a penny and scratch aluminum. Aluminum can't scratch copper. Now, diamond, being the hardest substance known to man, can scratch both of those, but nothing can scratch diamond. So hardness is another property. Copper can conduct heat and electric current very well. Copper and aluminum, something they have in common. They're both malleable. They can be hammered into sheets without breaking, which gives us these wonderful flat things to make round things out of, or roundish. Things like hardness, color, conductivity, malleability. Some examples of physical properties. Again, you might have heard of the difference between physical and chemical properties. We're looking at physical right here. Physical properties, it's a quality or condition that can be observed without changing the substance's composition. We can test conductivity of copper or aluminum. We can test hardness, but we don't have to destroy the sample. We don't have to send it through a chemical reaction to test this. We can observe it without actually harming the sample, if you will. And chemical reaction, we're going to get to that in this chapter. Chemical reactions will be actually changing one substance and doing that. You don't have to do that to test out physical properties. And these are good because we can help chemists identify substances. Colorless substance found to boil at 100 Celsius, melt at 0 Celsius, would likely be water. But if you tested it and found out it had a boiling point of 78 Celsius and a melting point at negative 117 Celsius, try converting that into Fahrenheit and see what you get. That would definitely not be water. It would probably be ethanol. Why? Because they have these, each substance has this characteristic melting and boiling point. It's going to be some really good identifiers. In this case, you wanted to distinguish oxygen from neon. They're both colorless gases, but neon has a much lower boiling point and melting point. They're both really cold, so really low. So you expect those to both be gases at room temperature. Let me pop over here in the middle here. I'm going to distinguish water from ethanol, different melting and boiling points. Let's see. Sulfur from gold, both yellow solids. However, if you looked at sulfur powder and gold has a different, you could say that's a different shade of gold. It's also different melting points. It takes more heat, obviously more heat, a higher temperature to melt gold, and to boil it if you wanted to. Wow, and it does take a lot of heat to boil gold. And it does take a moderate amount of heat. That's above melting. The melting point of sulfur is above water's boiling point. I definitely wouldn't want to melt it or boil it. It would smell really bad. Going back to my skunk analogy, it really smelled that bad. And again, we're talking about these guys at room temperature. We expect these gases, if they have a really low melting and boiling point, we expect them to be gases at room temperature. Liquids have a low melting point, but kind of a moderate boiling point, and it can vary. And then for solids, high melting point, high boiling point, as in really higher than room temperature, which would be about 37 Celsius. No, I'm sorry, that would be, room temperature would be somewhere between 20 and 25 Celsius. 37 is body temperature in Celsius. So depending on what circumstances you have 3 different words to refer to water. It could be in liquid water phase, it could be in solid ice, it could be in the gas phase, it could be steam. It can exist in 3 distinct different physical states. So can most other substances. And again, our major 3 states of matter, something you've heard for a long time: solid, liquid, and gas. A solid, that's a form of matter with a definite shape and volume. And again, we kind of assume that it's going to be kind of a nice crystal structure. We get to look at this a little deeper in chapter 13. Shape of a solid doesn't depend on the shape of its container because it's already kind of there. It's already kind of fixed. These particles are packed tightly together, often in an orderly arrangement. But one of the first things we find out is these particles are moving at some point. Maybe just jiggling back and forth in place, even with a solid. As a result, since these particles are kind of fixed in place, solids are almost incompressible. You can't squeeze a solid into a smaller volume. If you've ever seen the hydraulic press videos on YouTube, In addition, when we expand, when we heat solids, they expand just a little bit when heated. And of course, ice and water being sort of a weird exception. We get to talk about that later. But we think definite shape, definite volume, and incompressible. That's 3 characteristics we could use. As far as liquids, you think of going from solid to liquid. Of course, you think going from the solid phase to melting into a liquid. You can also go backwards. You can freeze a liquid into a solid or condense it down. No, not condensing it, but solidify. Particles and liquid, they're in close contact with each other, but the arrangement is not as rigid as a solid. The particles can flow past each other, which makes liquids fluid. Liquids can take the shape of the containers which they're placed. Here's some green liquid in an Erlenmeyer flask. We poured it in a different size, maybe a flatter pan, it would fill that container kind of in a flat way. The volume doesn't change. The shape can change, but the volume doesn't change. So we say indefinite shape, but a definite volume. What else can we say? Volume is also definite, fixed, or constant. Liquid is a form of matter. Again, indefinite shape, it can flow and has a fixed volume. That's not going to change, even when you heat them up a little bit. Well, they expand just a little bit, sort of like solids. It's something they have in common with solids. But liquids are also almost incompressible. Those molecules can flow past each other, but you really can't compress liquid particles into a smaller area. However, now we get to gases, and we have a whole chapter on gases. Just like liquids, gases can take the shape of a container. It's an indefinite volume, but gases can expand with temperature. Those particles can get farther apart to fill any volume. Here's the difference between liquid and gas. Again, gases will take the shape and the volume of a container. So if you put it in a I can't talk this late in the day, sorry guys. Bigger container, it'll fill the container, and the particles are usually much farther apart. Think about this as we've given these particles a lot of kinetic energy, a really high temperature. They're moving very quickly, and they're very far apart. And there's a big amount of space between the particles, which means since there's a big amount of space, gases can be easily compressed into a smaller volume. So out of the 3, gases are the only of the 3 states that can be compressible. But what's something that gases have in common with liquids, they're also considered fluids because these particles can flow. And again, when we talk about vapor and gas, I've already mentioned water vapor. In gas, we have a whole column in the periodic table of noble gases. We sometimes use these interchangeably, but you need to know the difference. Gas is something we'd say for like oxygen, neon, helium, stuff that we expect to be in the gas state at room temperature at all times. Vapor is something that's generally liquid or solid at room temperature, like water, but we've actually added enough heat to put it into the gas phase. If you always expect it to be a gas at room temperature, we call it a gas. But if it's actually forced by a higher temperature into the vapor phase or the gas phase, we call that vapor. So know the difference between gas and vapor. And what else can we figure out about all this stuff? Jumping back to solids, melting points. Gallium metal, big example, probably see it in every chemistry book. The melting point is 30 Celsius. Body temperature is 37 Celsius. So the heat from a person's hand can melt a sample of gallium. Shape changes during the melting process as the liquid begins to flow. The other thing is the composition. We don't change the fact that this is gallium metal. This is a whole bunch of gallium atoms. This is not a chemical reaction. It's just melting. It's just a phase change. And those phase changes are physical changes. During physical changes, some properties change, but the main composition of the material does not change. When you melt ice, it's still H2O. When you freeze water back into ice, it's still chemically H2O. Words like boil, freeze, melt, condense, these are used to describe physical changes. So are words like break, split, grind, cut, and crush. What's the big difference between these 2 sets of words? Each of those sets describes a different type of physical change. Boiling, freezing, melting, we can reverse that. Melting is an example of a reversible physical change. If we take liquid gallium and cool it below its melting point, as in put it back on a tabletop or back in a container, the liquid's going to become solid again. So that's reversible. However, all physical changes that involve a change from one state to another are reversible. Remember that. Now, cutting hair, filing nails, like you see here, cracking an egg. Remember Humpty Dumpty? All the king's horses, all the king's men couldn't put Humpty Dumpty back together again because that was an irreversible physical change. You can't just stick hair back together after you cut it and expect it to stay there. If you break a nail, you can use nail glue. I know, I've been there. Trying to use nail glue to stick it back together, but it's not going to work. You cut a nail, and you're just going to have to wait for hair and nails to grow back. Eggs, once they're cracked, they're cracked. You might as well just go ahead and make scrambled eggs or omelets. Those are irreversible physical changes. In our next video, we're going to get on digging into a little more about. In fact, I have my notebook over here. I'm going to talk about, if I could read it, mixtures. Next video will be about mixtures, and if you need anything, just send me an email. Bye.